Our next presenter is Bruce Yang. So if Bruce can come up to the front here. He's a second-year master's student. Is it Masters of Computing? Yeah. And specialising in AI. So his presentation is titled Calculation and Visualisation of Anatomical Inertial Parameters from raw CT scan data. Don't worry, you don't need to understand the title now. You will be a full bottle by the end of the presentation. His primary supervisor is Andrew Roll, with support from the School of Electrical Engineering, Computing and Mathematical Sciences, with additional support from Amity Campbell, Cian Williams, Sarah Stern, and also Hive support from Michael Ovens. This particular internship scholarship was supported by the ARC Centre for Excellence for the Digital Child.
So thank you for watching our internship presentation. My research project is the calculation and visualization of anatomical inertial parameters from raw CT scan data. And I will introduce three parts of our project: the background, our achievement, and the future direction. Now, the background. So in this slide, I will introduce the most important concept of our research, the initial parameters: mass, center of mass, and the moment of inertia. These three concepts are fundamental parameters in physical and engineering research. And mass, center of mass are well known, while the moment of inertia describe an object's resistance to rotation about a specific axis. And why do we need to calculate the initial parameters? These concepts are important in many fields, including robotics, mechanical design, and medical research. One basic application is motion analysis, which helps us understand movement in sports, biomechanics, and even animation. And we also can utilize the initial parameter in making a VR headset. And the VR headset is very important for children or adults to use. If the weight isn't balanced properly, they can be uncomfortable to wear. By adjusting the center of mass and the moment of inertia, we can make them feel comfortable. And also, finally, in rehabilitation technology, this parameter helps design better artificial limbs and vulnerable support devices, and also making movement smoother and recover more effective. So even though these ideas seem theoretical, they have a huge impact on the technology we use every day. So how to calculate the inertial parameter from the CT scan data? I draw a graph to show the methodology of our research. The journey begins with CT scanning, as shown in the bottom left image. This medical imaging technique extracts cross-sectional images of a human body, and also using X-rays. These raw CT images contain valuable anatomical details, but requires further processing to be useful for analysis and visualization. And also, once the CT scan data is obtained, the next step is the segmentation, extracting different anatomical structures from the scan. As illustrated in the figure, segmentation is performed on various body parts, such as the skull, head, soft tissue. Advanced imaging processing techniques such as thresholding, region growing, and even deep learning models can be used to achieve precise segmentation. And also, after segmentation, each identified structure is assigned a density value based on the CT scan segmentation results. This step is essential for biomechanical and medical calculations, as it helps determine the mass distribution of different tissues. Finally, the segmented and density assigned structures are reconstructed in a 3D model, enabling us to visualize and analyze the anatomical data. This step allows for precise calculation for mass distribution, center of mass, and mechanical properties, which are critical for application in surgery and biomechanics research. And the question is, manual segmentation took too much time. And also, there's a lack of software for one-click processing of CT data. And there's no direct API available for calculating initial parameter. So what is the purpose of our project? Our purpose for the project, we attempt to create a workflow for processing the CT data. The traditional method is too complex for the medical worker. So user-friendly software is very important and automatically solve complex data segmentation problems. No one would like to take much time to segment the CT scan results. An automated method would be great for medical workers. And also developing an engineering approach to automatically calculate the initial parameters because there is no direct API to deal with these issues. So the next step is our achievement, and I use a video to show what we did in this project.
Bodies are capable of performing an incredible range of movements: jumping, running, twisting, and more. Behind these motions lies a complex interplay of forces, with inertia parameters playing a crucial role. If we could visualize and calculate these parameters, it would provide invaluable insights into understanding the human body. To visualize the 3D structure of the human body and calculate inertia parameters, we have developed a tool powered by the advanced AI capabilities of Total Segmentator and CT imaging results. AutoSlicer, a powerful software for human structure visualization and inertia parameter calculation, allowing you to achieve visualization and calculation with just 4 lines of code. AutoSlicer can quickly create 3D anatomical structures from CT scan results. The 3D models created by AutoSlicer not only have surface features, but also include the detailed subdivision of each tissue within the entire anatomical structure. AutoSlicer can also automatically create density values for different anatomical tissues. In this 3D model, the red regions indicate higher density, while the blue regions represent lower density. In addition, we can use the calculation feature of AutoSlicer to measure the position of the center of mass. AutoSlicer can also calculate important physical parameters of these human structures, including mass, volume, and moments of inertia. By visualizing the calculation of inertia parameters, we enable a deeper understanding of how these parameters contribute to safeguarding children's health, assisting medical professionals in designing more effective patient recovery processes, and advancing the practical development of bionic robots.
So in this section, I will introduce the main function of AutoSlicer, a Python plugin for faster computation and segmentation of CT scan data, and enabling efficient processing, analysis, and visualization of medical imaging for research applications. It also allows for the rapid generation of 3D models. And here is the main function. The biggest advantage of AutoSlicer is that it can convert CT scan data into a 3D model with just 1 click. You don't need to focus on the details of AutoSlicer. You only need to pay attention to the input and the output. AutoSlicer works like a black box. And AutoSlicer can recognize 118 structures of human body by using Total Segmentator's AI. Currently, we have integrated into Total Segmentator, which is a highly useful tool to process the CT scan results. And AutoSlicer can efficiently calculate the initial parameter. The second major advantage of AutoSlicer is the ability to automatically assign density to each anatomical structure, ensuring accurate mass distribution for biomechanical analysis. By integrating advanced segmentation and density mapping techniques, AutoSlicer provides precise physical property calculations without requiring manual adjustment, making it highly efficient for medical and research applications. And also, now let's talk about how simple it is to install and use AutoSlicer. First, installation is super easy. You don't need to run a single command, and it's easy to go. You can use this command to download the AutoSlicer from the Python. And once installed, using AutoSlicer is very easy. You don't have to worry about technical details. AutoSlicer will handle everything. It automatically processes the data segments, the anatomical structures, assign density values, and calculate the key biomechanical parameters. AutoSlicer is designed to be user-friendly and efficient, making it a powerful medical imaging and analysis tool. And AutoSlicer can be compatible for different anatomical structures. First, AutoSlicer allows to extract specific tissues by setting a threshold range value. We can extract the soft tissue and not including any other part of the body. Another powerful feature is the density assignment. AutoSlicer lets you define the density of different anatomical structures, ensuring accurate math and initial calculations. This makes it highly flexible for various biomechanical and medical research applications. With these tailor-made options, AutoSlicer precise and adaptive analysis for different needs. And here is some result of AutoSlicer. And our data from the visible human project and consisting of 2 cadavers, 1 male and 1 females. And you can see the graph, and you can see the skull and the brain and the vertebra and the soft tissue, and you can see the complex skull structure in human body. And we also can see the different color of the vertebra. And in the center, this is we use the power view to show the 3D structure. We can see the different layer of this model. And this is the male. You can see the different density for this head. And actually, this is a cadaver. And we in the future, we will try more data to show our AutoSlicer's results. And AutoSlicer is able to present the center of mass. We can observe the center of mass created by the AutoSlicer, the red ball and the green 3D model in this box. And it's easily to show the center of mass. And the next one is future direction. Next, we need to find more public data set to test the AutoSlicer, because actually this is a software and a plug-in for some medical research. So we need to more test, and this one would be great for some medical workers. And we also need to find a better segmentation algorithm to replace the total segmentator. Exploring more advanced segmentation model can enhance the precision, efficiency, and compatibility with various data sets. Because now we did is a combination and integration for some different medical API. So in the future, we need to try more advanced technique algorithms to improve our project. And also, we need to add a user-friendly interface to suit different users. We need to develop a user-friendly interface, and I think this one make AutoSlicer can accessible to both researchers and medical professionals, and this one can improving our usability and workflow. And here's the acknowledgement. I would like to take a moment to thank my supervisors for their support and guidance throughout this research. And their expertise has been very important to this project. And I also want to thank the ARC Center of Excellence for the Digital Child for funding this research. And finally, thank you all for listening.